Chapter 9, Force and Laws of Motion. In the previous chapter, we described the motion of an object along a straight line in terms of its position, velocity and acceleration. We saw that such a motion can be uniform or non-uniform. We have not yet discovered what causes the motion. Why does the speed of an object change with time? Do all motions require a cause? If so, what is the nature of this cause? In this chapter, we shall make an attempt to quench all such curiosities. For many centuries, the problem of motion and its causes had puzzled scientists and philosophers. A ball on the ground, when given a small hit, does not move forever. Such observation suggests that rest is the natural state of an object. This remained the belief until Galileo Galilei and Isaac Newton developed an entirely different approach to understand motion. A. The trolley moves along the direction we push it. B. The drawer is pulled. C. The hockey stick hits the ball forward. Figure, pushing, pulling or hitting objects change their state of motion. In our everyday life, we observe that some effort is required to put a stationary object into motion or to stop a moving object. We ordinarily experience this as a muscular effort and say that we must push or hit or pull on an object to change its state of motion. The concept of force is based on this push, hit or pull. Let us now ponder about a force. What is it? In fact, no one has seen, tested or felt a force. However, we always see or feel the effect of a force. It can only be explained by describing what happens when a force is applied to an object. Pushing, hitting and pulling of object are all ways of bringing objects in motion. Figure, they move because we make a force act on them. From your studies in earlier classes, you are also familiar with the fact that a force can be used to change the magnitude or velocity of an object. That is, to make the object move faster or slower, or to change its direction of motion. We also know that a force can change the shape and size of objects. Figure A. B. Figure A spring expands on application of force. B. A spherical rubber ball becomes oblong as we apply force on it. 9.1 Balanced and unbalanced forces. Figure shows a wooden block on a horizontal table. Two strings X and Y are tied to the two opposite faces of the block as shown. If we apply a force by pulling the string X, the block begins to move to the right. Similarly, if we pull the string Y, the block moves to the left. But if the block is pulled from both the sides with equal forces, the block will not move. Such forces are called balanced forces and do not change the state of rest or of motion of an object. Now let us consider a situation in which two opposite forces of different magnitude pull the block. In this case, the block would begin to move in the direction of the greater force. Thus, the two forces are not balanced and the unbalanced force acts in the direction the block moves. This suggests that an unbalanced force acting on an object brings it in motion. X, Y. Figure two forces acting on a wooden block. What happens when some children try to push a box on a rough floor? If they push the A, B, C. Figure. Box with a small force, the box does not move because of friction acting in a direction opposite to the push. Figure A. This friction force arises between two surfaces in contact, in this case between the bottom of the box and floor rough surface. It balances the pushing force and therefore the box does not move. In figure B, the children push the box harder but the box still does not move. This is because the friction force still balances the pushing force. If the children push the box harder still, the pushing force becomes bigger than the friction force. Figure C. There is an unbalanced force, so the box starts moving. What happens when we ride a bicycle? When we stop pedaling, the bicycle begins to slow down. This is again because of the friction forces acting opposite to the direction of motion. In order to keep the bicycle moving, we have to start pedaling again. It thus appears that an object maintains its motion under the continuous application of an unbalanced force. However, it is quite incorrect. An object moves with a uniform velocity when the forces, pushing force and frictional force acting on the object are balanced and there is no net external force on it. If an unbalanced force is applied on the object, there will be a change either in its speed or in the direction of its motion. Thus, to accelerate the motion of an object, an unbalanced force is required and the change in its speed or in the direction of motion would continue as long as this unbalanced force is applied. However, if this force is removed completely, the object would continue to move with the velocity it has acquired till then. 9.2 First law of motion. By observing the motion of objects on an inclined plane, Galileo deduced that objects move with a constant speed when no force acts on them. He observed that when a marble rolls down an inclined plane, its velocity increases. Figure A. In the next chapter, you will learn that the marble falls under the unbalanced force of gravity as it rolls down and attains a definite velocity. By the time it reaches the bottom, its velocity decreases when it climbs up as shown in figure B. Figure C shows a marble resting on an ideal frictionless plane inclined on both sides. Galileo argued that when the marble is released from left, it would roll down the slope and go up on the opposite side to the same height from which it was released. If the inclinations of the planes on both sides are equal, then the marble will climb the same distance that it covered while rolling down. If the angle of inclinations of the right side plane were gradually decreased, then the marble would travel further distances till it reaches the original height. If the right side plane were ultimately made horizontal, that is, the slope is reduced to zero, the marble would continue to travel forever, trying to reach the same height that it was released from. The unbalanced forces on the marble in this case are zero. It thus suggests that an unbalanced external force is required to change the motion of the marble, but no net force is needed to sustain the uniform motion of the marble. In practical situations, it is difficult to achieve a zero unbalanced force. This is because of the presence of the frictional force acting opposite to the direction of motion. Thus, in practice, the marble stops after traveling some distance. The effect of the frictional force may be minimized by using a smooth marble and a smooth plane and providing a lubricant on top of the planes. A, B, C. A downward motion. B. The upward motion of a marble on an inclined plane. And C. On a double inclined plane. Newton further studied Galileo's ideas on force and motion and presented three fundamental laws that govern the motion of objects. These three laws are known as Newton's laws of motion. The first law of motion is stated as: an object remains in a state of rest or of uniform motion in a straight line unless compelled to change that state by an applied force. In other words, all objects resist a change in their state of motion. In a qualitative way, the tendency of undisturbed objects to stay at rest or to keep moving with the same velocity is called inertia. This is why the first law of motion is also known as the law of inertia. Certain experiences that we come across while traveling in a motor car can be explained on the basis of the law of inertia. We tend to remain at rest with respect to the seat until the driver applies a braking force to stop the motor car. With the application of brakes, the car slows down, but our body tends to continue in the same state of motion because of its inertia. A sudden application of brakes may thus cause injury to us by Galileo Galilei, 1564 to 1642. Galileo Galilei was born on 15 February 1564 in Pisa, Italy. Galileo, right from his childhood, had interest in mathematics and natural philosophy. But his father, Vincenzo Galileo, wanted him to become a medical doctor. Accordingly, Galileo enrolled himself for a medical degree at the University of Pisa in 1581, which he never completed because of his real interest in mathematics. In 1586, he wrote his first scientific book, The Little Balance, La Balancetta, in which he described Archimedes' methods of finding the relative densities or specific gravities of substances using a balance in 1589. In his series of Essays de Motu, he presented his theories about falling objects using an inclined plane to slow down the rate of descent. In 1592, he was appointed professor of mathematics at the University of Padua in the Republic of Venice. Here he continued his observation on the theory of motion, and through his study of inclined planes and the pendulum formulated the correct law for uniformly accelerated objects that the distance the object moves is proportional to the square of the time taken. Galileo was also a remarkable craftsman. He developed a series of telescopes whose optical performance was much better than that of other telescopes available during those days. Around 1640, he designed the first pendulum clock. In his book, A Starry Messenger, on his astronomical discoveries, Galileo claimed to have seen mountains on the moon. The Milky Way, made up of tiny stars and four small bodies orbiting Jupiter. In his books, Discourse on Floating Bodies and Letters on the Sunspots, he disclosed his observations of sunspots. Using his own telescopes and through his observations on Saturn and Venus, Galileo argued that all the planets must orbit the Sun and not the Earth, contrary to what was believed at that time. Impact or collision with the panels in front, safety belts are worn to prevent such accidents. Safety belts exert a force on our body to make the forward motion slower. An opposite experience is encountered when we are standing in a bus and the bus begins to move suddenly. Now we tend to fall backwards. This is because the sudden start of the bus brings motion to the bus as well as to our feet in contact with the floor of the bus. But the rest of our body opposes this motion because of its inertia. When a motor car makes a sharp turn at a high speed, we tend to get thrown to one side. This can again be explained on the basis of the law of inertia. We tend to continue in our straight line motion when an unbalanced force is applied by the engine to change the direction of motion of the motor car. We slip to one side of the seat due to the inertia of our body. The fact that a body will remain at rest unless acted upon by an unbalanced force can be illustrated through the following activities. Activity 9.1. Do this. Make a pile of similar carom coins on a table as shown in figure. Attempt a sharp horizontal hit at the bottom of the pile using another carom coin or the striker. If the hit is strong enough, the bottom coin moves out quickly. Once the lowest coin is removed, the inertia of the other coins makes them fall vertically on the table. Figure: only the carom coin at the bottom of a pile is removed when a fast moving carom coin or striker hits it. Activity 9.2. Do this. Set a 5 rupee coin on a stiff card covering an empty glass tumbler standing on the table as shown in figure. Give the card a sharp horizontal flick with a finger. If we do it first, then the card shoots away, allowing the coin to fall vertically into the glass tumbler due to its inertia. The inertia of the coin tries to maintain its state of rest even when the card flows up. Figure: when the card is flicked with the finger, the coin placed over it falls in the tumbler. Activity 9.3. Do this. Place a water-filled tumbler on a tray. Hold the tray and turn around as fast as you can. We observe that the water spills. Why? Observe that a groove is provided in a saucer for placing the teacup. It prevents the cup from toppling over in case of sudden jerks. Nine point three. Inertia and mass. All the examples and activities given so far illustrate that there is a resistance offered by an object to change its state of motion. If it is at rest, it tends to remain at rest. If it is moving, it tends to keep moving. This property of an object is called its inertia. Do all bodies have the same inertia? We know that it is easier to push an empty box than a box full of books. Similarly, if we kick a football, it flies away. But if we kick a stone of the same size with equal force, it hardly moves. We may, in fact, get an injury in our foot while doing so. Similarly, in activity, instead of a 5 rupees coin, if we use a 1 rupee coin, we find that a lesser force is required to perform the activity. A force that is just enough to cause a small car to pick up a large velocity will produce a negligible change in the motion of a train. This is because in comparison to the car, the train has a much lesser tendency to change its state of motion. Accordingly, we say that the train has more inertia than the car. Clearly, heavier or more massive objects offer larger inertia. Quantitatively, the inertia of an object is measured by its mass. We may thus relate inertia and mass as follows. Inertia is the natural tendency of an object to resist a change in its state of motion or of rest. The mass of an object is a measure of its inertia. Questions 1, 2, 3, 4. Comment this. 9.4 Second law of motion. The first law of motion indicates that when an unbalanced external force acts on an object, its velocity changes, that is, the object gets an acceleration. We would now like to study how the acceleration of an object depends on the force applied to it and how we measure a force. Let us recount some observations from our everyday life. During the game of table tennis, if the ball hits a player, it does not hurt him. On the other hand, when a fast moving cricket ball hits a spectator, it may hurt him. A truck at rest does not require any attention when parked along a roadside, but a moving truck, even at speeds as low as 5 meters per second, may kill a person standing in its path. A small mass, such as a bullet, may kill a person when fired from a gun. This observation suggests that the impact produced by the objects depends on their mass and velocity. Similarly, if an object is to be accelerated, we know that a greater force is required to give a greater velocity. In other words, there appears to exist some quantity of importance that combines the object's mass and its velocity. One such property, called momentum, was introduced by Newton. The momentum p of an object is defined as the product of its mass m and velocity v, that is p equal to mv. Momentum has both direction and magnitude. Its direction is the same as that of velocity v. The SI unit of momentum is kilogram meter per second, kilogram meter per second. Since the application of an unbalanced force brings a change in the velocity of the object, it is therefore clear that a force also produces a change of momentum. Let us consider a situation in which a car with a dead battery is to be pushed along a straight road to give it a speed of 1 meter per second, which is sufficient to start its engine. If one or two persons give a sudden push, unbalanced force to it, it hardly starts. But a continuous push over some time results in a gradual acceleration of the car to this speed. It means that the change of momentum of the car is not only determined by the magnitude of the force but also by the time during which the force is exerted. It may then also be concluded that the force necessary to change the momentum of an object depends on the time rate at which the momentum is changed. The second law of motion states that the rate of change of momentum of an object is proportional to the applied unbalanced force in the direction of force. 9.4.1 Mathematical formulation of second law of motion. Suppose an object of mass m is moving along a straight line with an initial velocity u. It is uniformly accelerated to velocity v in time t by the application of a constant force F throughout the time t. The initial and final momentum of the object will be P1 equal to mu and P2 equal to mv respectively. The change is in momentum proportional to P2 minus P1 proportional to mv minus mu proportional to m into v minus u. The rate of change of momentum proportional to m into v minus u by t, or the applied force F proportional to m into v minus u by t, F equal to km into v minus u by t equal to kma. Here A equal to v minus u by t is the acceleration, which is the rate of change of velocity. The quantity k is a constant of proportionality. The SI units of mass and acceleration are kg and meter per second square respectively. The unit of force is so chosen that the value of the constant k becomes 1. For this, one unit of force is defined as the amount that produces an acceleration of 1 meter per second square in an object of 1 kg mass. That is, one unit of force equal to k into 1 kg into 1 meter per second square. Thus, the value of K becomes 1 from equation F equal to ma. The unit of force is kilogram meter per second square or Newton, which has the symbol N. The second law of motion gives us a method to measure the force acting on an object as a product of its mass and acceleration. The second law of motion is often seen in action in our everyday life. Have you noticed that while catching a fast moving cricket ball, a fielder in the ground gradually pulls his hands backward with the moving ball? In doing so, the fielder increases the time during which the high velocity of the moving ball decreases to zero. Thus, the acceleration of the ball is decreased and therefore the impact of catching the fast moving ball is also reduced. If the ball is stopped suddenly, then its high velocity decreases to zero in a very short interval of time. Thus, the rate of change of momentum of the ball will be large. Therefore, a large force would have to be applied for holding the catch that may hurt the palm of the fielder. In a high jump athletic event, the athletics are made to fall either on a cushioned bed or on a sand bed. This is to increase the time of the athlete's fall to stop after making the jump. This decreases the rate of change of momentum and hence the force. Try to ponder how a karate player breaks a slab of ice with a single blow. Figure: a fielder pulls his hand gradually. Figure: a fielder pulls his hands gradually with the moving ball while holding a catch. The first law of motion can be mathematically stated from the mathematical expression for the second law of motion. Equation is F equal to ma, or F equal to m of v minus u by t, or Ft equal to mv minus mu. That is when F equal to 0, v equal to u for whatever time t is taken. This means that the object will continue moving with uniform velocity u throughout the time t. If u is 0, then v will also be 0. That is, the object will remain at rest. Example 9.1. A constant force acts on an object of mass 5 kg for a duration of 2 seconds. It increases the object's velocity from 3 meter per second to 7 meter per second. Find the magnitude of the applied force. Now, if the force was applied for a duration of 5 seconds, what would be the final velocity of the object? Solution. We have been given that u equal to 3 meter per second and v equal to 7 meter per second, t equal to 2 second and m equal to 5 kg. From equation we have F equal to mv minus u by t. Substitution of values in this relation gives F equal to 5 kg of 7 meter per second minus 3 meter per second by 2 seconds equal to 10 Newton. Now, if this force is applied for a duration of 5 seconds, t equal to 5 seconds, then the final velocity can be calculated by rewriting equation as v equal to u plus ft by m. On substituting the values of u, f, m and t, we get the final velocity v equal to 13 meter per second. Example 9.2. Which would require a greater force accelerating a 2 kg mass at 5 meter per second square or a 4 kg mass at 2 meter per second square? Solution. From equation we have F equal to ma. Here we have m1 equal to 2 kg, a1 equal to 5 meter per second square and m2 equal to 4 kg, a2 equal to 2 meter per second square. Thus F1 equal to m1 a1 equal to 2 kg into 5 meter per second square equal to 10 Newton and F2 equal to m2 a2 equal to 4 kg into 2 meter per second square equal to 8 Newton. implies that F1 greater than F2, thus accelerating a 2 kg mass at 5 meter per second square would require a greater force. Example 9.3. A motor car is moving with a velocity of 108 km per hour and it takes 4 seconds to stop after the brakes are applied. Calculate the force exerted by the brakes on the motor car if its mass along with the passengers is 1000 kg. Solution. The initial velocity of the motor car u equal to 108 km per hour equal to 108 into 1000 meter per 60 into 60 second equal to 30 meter per second, and the final velocity of the motor car v equal to 0 meter per second. The total mass of the motor car along with its passenger equal to 1000 kg and the time taken to stop the motor car t equal to 4 seconds. From equation we have the magnitude of the force F applied by the brakes as m of v minus u by t. On substituting the values we get F equal to 1000 kg into 0 minus 30 meter per second per 4 second equal to minus 7500 kg meter per second square or minus 7500 Newton. The negative sign tells us that the force exerted by the brakes is opposite to the direction of motion of the motor cars. Example 9.4. A force of 5 Newton gives a mass m1 an acceleration of 10 meter per second square and a mass m2 an acceleration of 20 meter per second square. What acceleration would it give if both the masses were tied together? Solution. From equation we have m1 equal to f by a1 and m2 equal to f by a2. Here a1 equal to 10 meter per second square, a2 equal to 20 meter per second square and f equal to 5 Newton. Thus m1 equal to 5 Newton per 10 meter per second square equal to 0.50 kg and m2 equal to 5 Newton per 20 meter per second square equal to 0.25 kg. If the two masses were tied together, the total mass m would be m equal to 0.50 kg plus 0.25 kg equal to 0.75 kg. The acceleration produced in the combined mass by the 5 Newton force would be a equal to f by m equal to 5 Newton per 5 Newton by 0.75 kg equal to 6.67 meter per second square. Example 9.5. The velocity time graph of a ball of mass 20 gram moving along a straight line on a long table is given in figure. Velocity centimeter per second 5, 10, 15, 20, 25 times second 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Figure. How much forces does the table exert on the ball to bring it to rest? Solution. The initial velocity of the ball is 20 cm per second. Due to the frictional force exerted by the table, the velocity of the ball decreases down to 0 in 10 seconds. Thus, u equal to 20 cm per second, v equal to 0 cm per second and t equal to 10 seconds. Since the velocity time graph is a straight line, it is clear that the balls move with a constant acceleration. The acceleration a is a equal to v minus u by t equal to 0 cm per second minus 20 cm per second by 10 second equal to minus 2 cm per second square equal to minus 0.02 meter per second square. The force exerted on the ball F is F equal to ma equal to 20 by 1000 kg into minus 0.02 meter per second square equal to minus 0.0004 Newton. The negative sign implies that the frictional force exerted by the table is opposite to the direction of motion of the ball. Nine point five. Third law of motion. The first two laws of motion tell us how an applied force changes the motion and provide us with a method of determining the force. The third law of motion states that when one object exerts a force on another object, the second object instantaneously exerts a force back on the first. These two forces are always equal in magnitude but opposite in direction. These forces act on different objects and never on the same object. In the game of football, sometimes we, while looking at the football and trying to kick it with a greater force, collide with a player of the opposite team. Both feel hurt because each applies a force to the other. In other words, there is a pair of forces and not just one force. The two opposing forces are also known as action and reaction forces. Let us consider two spring balances connected together as shown in figure. The fixed end of balance B is attached with a rigid support like a wall when a force is applied through the free end of spring balance A. It is observed that both the spring balances show the same readings on their scales. It means that the force exerted by spring balance A on balance B is equal but opposite in direction to the force exerted by the balance B on balance A. Any of these two forces can be called as action and the other as reaction. This gives us an alternative statement of the third law of motion, that is, to every action that there is an equal and opposite reaction. However, it must be remembered that the action and reaction always act on two different objects simultaneously. A. B. Figure: action and reaction forces are equal and opposite. Suppose you are standing at rest and intend to start walking on a road, you must accelerate, and this requires a force in accordance with the second law of motion. Which is this force? Is it the muscular effort you exert on the road? Is it in the direction we intend to move? No. You push the road below backwards. The road exerts an equal and opposite force on your feet to make you move forward. It is important to note that even though the action and reaction forces are always equal in magnitude, these forces may not produce accelerations of equal magnitudes. This is because each force acts on a different object that may have a different mass. When a gun is fired, it exerts a forward force on the bullet. The bullet exerts an equal and opposite force on the gun. This results in the recoil of the gun figure. Since the gun has a much greater mass than the bullet, the acceleration of the gun is much less than the acceleration of the bullet. The third law of motion can also be illustrated when a sailor jumps out of a rowing boat. As the sailor jumps forward, the force on the board moves it backwards. Figure: accelerating force on the bullet, recoil force of the gun. Figure: a forward force on the bullet and recoil of the gun. Figure: as the sailor jumps in forward direction, the boat moves backward. Activity 9.4. Do this. Request two children to stand on two separate cards as shown in figure. Give them a bag full of sand or some other heavy object. Ask them to play a game of catch with the bag. Does each of them experience an instantaneous force as a result of throwing the sand back? You can paint a white line on cartwheels to observe the motion of the two cards when the children throw the bag towards each other. Figure: now place two children on one card and one on another card. The second law of motion can be seen, as this arrangement would show different acceleration for the same force. The card shown in this activity can be constructed by using a 12 mm or 18 mm thick plywood board of about 50 cm into 100 cm with two pairs of hard ball bearing wheels. skate wheels are good to use. Skateboards are not as effective because it is difficult to maintain a straight line motion. 9.6 Conservation of momentum. Suppose two objects, two balls A and B, say of masses ma and mb are traveling in the same direction along a straight line at different velocities ua and ub respectively, figure A, and there are no other external unbalanced forces acting on them. Let ua greater than ub and the two balls collide with each other as shown in figure B. During collision, which lasts for a time t, the ball A exerts a force FAV on ball B and the ball B exerts a force FBA on ball A. Suppose VA and VB are the velocities of the two balls A and B after the collisions, respectively, figure C. A, MA, MB, UA before collisions, UB, B, AB, FAB, FBA, C. After collisions, MA, VA, MB, VB. Figure conservation of momentum in collision of two balls. From equation, the momenta plural of momentum of ball A before and after the collision are MAUA and MAVA respectively. The rate of change of its momentum or FAB during the collision will be MAVA minus UA by T. Similarly, the rate of change of momentum of ball B equal to FBA during the collision will be MB VB minus UB by T. According to the third law of motion, the force FAB exerted by ball A on ball B and the force FBA exerted by the ball B on ball A must be equal and opposite to each other. Therefore, FAB equal to minus FBA or MA VA minus UA by T equal to minus MB VB minus UB by T. This gives MA UA plus MB UB equal to MA VA plus MB VB. Since MA UA plus MB UB is the total momentum of the two balls A and B before the collision and MA VA plus MB VB is their total momentum after the collision, from equation we observe that the total momentum of the two balls remains unchanged or conserved provided no other external force acts. As a result of this ideal collisions experiment, we say that the sum of momenta of the two objects before collision is equal to the sum of momenta after the collisions provided there is no external unbalanced force acting on them. This is known as the law of conservation of momentum. This statement can alternatively be given as the total momentum of the two objects is unchanged or conserved by the collision. Activity 9.5. Do this. Take a big rubber balloon and inflate it fully. Tie its neck using a thread. Also using adhesive tape, fix a straw on the surface of this balloon. Pass a thread through the straw and hold one end of the thread in your hand or fix it on the wall. Ask your friend to hold the other end of the thread or fix it on a wall at some distance. This arrangement is shown in figure. Now remove the thread tied on the neck of balloon. Let the air escape from the mouth of the balloon. Observe the direction in which the straw moves. A straw, air, balloons. Figure. Activity 9.6. Do this. Take a test tube of good quality glass material and put a small amount of water in it. Place a stop cork at the mouth of it. Now suspend the test tube horizontally by two strings or wires as shown in figure. Heat the test tube with a burner until water vaporizes and the cork blows out. Observe that the test tube recoils in the direction opposite to the direction of the cork. Figure. Also observe the difference in the velocity the cork appears to have and that of the recoiling test tube. Example 9.6. A bullet of mass 20 gram is horizontally fired with a velocity 150 meter per second from a pistol of mass 2 kg. What is the recoil velocity of the pistol? Solution. We have the mass of bullet M1 equal to 20 gram equal to 0.02 kg and the mass of the pistol M2 equal to 2 kg. Initial velocities of the bullet U1 and pistol U2 equal to 0 respectively. The final velocity of the bullet V1 equal to plus 150 meter per second. The direction of bullet is taken from left to right positive by convention. Figure. Let V be the recoil velocity of the pistol. Total momentum of the pistol and bullet before the fire when the gun is at rest equal to 2 plus 0.02 kg into 0 meter per second equal to 0 kg meter per second. Total momentum of the pistol and bullet after it is fired equal to 0.02 kg into plus 150 meter per second plus 2 kg into v meter per second equal to 3 plus 2v kg meter per second. According to the law of conservation of momentum, total momentum after the fire, total momentum before the fire, 3 plus 2v equal to 0 implies v equal to minus 1.5 meter per second. Negative sign indicates that the direction in which the pistol would recoil is opposite to that of bullet, that is right to left. A. Before firing. After firing, V 150 meter per second 20 gram to kg. B. Figure recoil of a pistol. (40 kg 5 meter per second 3 kg curved. A. B. 43 kg V. Figure the girl jumps onto the cart. Example 9.7. A girl of mass 40 kg jumps with a horizontal velocity of 5 meter per second onto a stationary cart with frictionless wheels. The mass of the cart is 3 kg. What is her velocity as the cart starts moving? Assume that there is no external unbalanced force working in the horizontal direction. Solution. Let V be the velocity of the girl on the cart as the cart starts moving. The total momentum of the girl and cart before the interaction equal to 40 kg into 5 meter per second plus 3 kg into 0 meter per second equal to 200 kilogram meter per second. Total momentum after the interaction equal to 40 plus 3 kg into v meter per second equal to 43 v kilogram meter per second. According to the law of conservation of momentum, the total momentum is conserved during the interaction, that is 43 v equal to 200 implies v equal to 200 by 43 equal to plus 4.65 meter per second. The girl on cart would move with a velocity of 4.65 meter per second in the direction in which the girl jumped. Figure. Example 9.8. Two hockey players of opposite team, while trying to hit a hockey ball on the ground, collide and immediately become entangled. One had a mass of 60 kg and was moving with a velocity 5 meter per second, while the other has a mass of 55 kg and was moving faster with a velocity 6 meter per second towards the first player. In which direction and with what velocity will they move after they become entangled? Assume that the frictional force acting between the feet of the two players and ground is negligible. Solution: 60 kg 5 meter per second, 55 kg 6 meter per second. A. B. 115 kg. B. Figure: a collision of two hockey players, A before collision and B after collisions. Let the first player be moving from left to right. By convention, left to right is taken as the positive direction and thus right to left is the negative direction. Figure: if symbols M and U represent the mass and initial velocity of the two players respectively, subscript 1 and 2 in these physical quantities refer to the two hockey players. Thus, M1 equal to 60 kg, U1 equal to plus 5 meter per second and M2 equal to 55 kg, U2 equal to minus 6 meter per second. The total momentum of the two players before the collision equal to 60 kg into plus 5 meter per second plus 55 kg into minus 6 meter per second equal to minus 30 kg meter per second. If v is the velocity of the two entangled players after the collision, the total momentum them equal to m1 plus m2 into v equal to 60 plus 55 kg into v meter per second equal to 115 into v kg meter per second, equating the moment of the system before and after collision. In accordance with the law of conservation of momentum, we get v equal to minus 30 by 115 equal to minus 0.26 meter per second. Thus, the two entangled players would move with velocity 0.26 meter per second from right to left, that is, in the direction the second player was moving before the collision. Questions 1, 2, 3. Comment this. 4. Comment this. Conservation laws. All conservation laws such as conservation of momentum, energy, angular momentum, charge, etc. are considered to be fundamental laws in physics. These are based on observation and experiment. It is important to remember that a conservation law cannot be proved. It can be verified or disproved by experiments. An experiment whose result is in conformity with the law verifies or substantiates the law. It does not prove the law. On the other hand, a single experiment whose result goes against the law is enough to disprove it. The law of conservation of momentum has been deduced from large number of observations and experiments. This law was formulated nearly 3 centuries ago. It is interesting to note that not a single situation has been realized so far which contradicts this law. Several experiences of everyday life can be explained on the basis of the law of conservation of momentum. What you have learnt. First law of motion: an object continues to be in a state of rest or of uniform motion along a straight line unless acted upon by an unbalanced force. The natural tendency of objects to resist a change in their state of rest or of uniform motion is called inertia. The mass of an object is a measure of its inertia. Its SI unit is kilogram kg. Force of friction always opposes motion of objects. Second law of motion: the rate of change of momentum of an object is proportional to the applied unbalanced force in the direction of the force. The SI unit of force is kilogram meter per second square. This is also known as Newton and represented by the symbol N. A force of 1 Newton produces an acceleration of 1 meter per second square on an object of mass 1 kg. The momentum of an object is the product of its mass and velocity and has the same direction as that of the velocity. Its SI unit is kilogram meter per second. Third law of motion: to every action there is an equal and opposite reaction, and they act on two different bodies. In an isolated system where there is no external force, the total momentum remains conserved. Exercises: do this and comment this. Additional exercises: do this and comment this.